go through parallel binary search. Right? So what is parallel binary search? The idea is that okay, so I'll give you guys a while to read this question first. Okay, so this is the input. Okay, so the input is nm followed by, okay, so now in this case we have three states, and we have three with m sectors. Okay, set m sectors. So m sectors is like on the ground, right? It's like the sectors are literally an array, right? Then each sector has okay, so each sector has, okay, so OI is the states owning stations in successive sectors. Okay, so each sector, right? These are the sectors. Each sector belongs to a state. In this case, you have three states, right? Three states labeled. I'm just gonna label them. In order to avoid being confused, I'm just gonna label them A, B, C. Okay. So then the next m integers here, right? This array, right? In this case, 1, 2, 3 corresponding to A, B, C will be the states that the sectors belong to. So in this case, it's A, C, B, A, C. Okay. So in this case, it's this, right? The second row of input is that, right? So the first one is N, second one is M sectors, then A, B, A, C, B, A, C. Then the next one will be, so each state, right? Each state. So now we know each sector belongs to each state, but each state has a certain threshold. Each state has a certain threshold, meaning that the meteor samples that they intend to gather, right? So they want to gather at least how many meteor samples. So in this case, state A wants 10 meteor samples, state B wants 7, 5, and state C wants 7, right? As you see in the third row of input over here. Okay, and so now we have the setup over here. Each state owns a few sectors, right? In this, but they're not necessarily contiguous, right? And each sector would have meteors raining on it later, right? But each state wants to collect some amount of meteors. So for example, if one meteor rain here and two meteor rain here, right, then A has a total of 3 meteors, right? So they can collect their sectors are kind of like umbrellas or pails collecting meteors, and then they want to sum up all the sectors that they own, and then they want to collect a minimum amount of meteors, right, to do research. Then okay, then following K lines, right? Following K lines would be L, R, and A, right? So referring to range L to R. So in this case, the first one is 4 to 2, right? Which means that a meteor raining down from here, from L to R, right? So if R is less than L, then it goes one way round, right? So in this case, it's L to R, and then it plus 4 for each one. So plus 4, plus 4, plus 4, plus 4, right? So now in total, after the first meteor shower, so the K meteor showers, right? The first one being this one, and then the I'll just put after K equals to 1, after K equals to 2, after K equals to 3, right? So after K equals to 1, after K equals to 2, or K equals to 3, then in this case, we can make a table, right? So the goal, this is the goal, right? And then after each meteor shower, the thing would have some amount of meteors. So after K equals to 1, you have A has a total of 8, B has a total of 0, and C has a total of 8. Okay, so any questions regarding the input? Okay, so for each state, right, for each A, B, C state, right, we're gonna ask which meteor shower, at which time, right, at which time would they be happy. So in this case, after the first meteor shower, C is already happy, right? And that's why we see for the input data, you see C is happy over here. And okay, so if you continue doing the input, next one is 3, it's 1, 3, 1. So next one, 1, 3, 1, it will mean, okay, so I'm gonna erase all this, and 1, 3, 1 meaning that it's gonna shower from 1 to 3 plus 1 plus 1 plus 1, like that. So after the meteor shower, it's going to be, after K equals to 2, it'll be here will be 9, here will be 1, and here will be here we don't really need to care, right? Because it was already satisfied here. C was already happy, right? So in this case, nobody is happy yet, right? A and B is not happy yet. And after k equals to 3, so let's do k equals to 3. K equals to 3 would have 3 to 5, and there's plus 2, right? So there's I'll put it in red, right? Plus 2, plus, sorry, no, that's not in red. I'll put it in red, plus 2, plus 2, plus 2, right? So after that, this will become, A would then have 11, B would then have 3, and C, once again, we don't really care, right? And so that's why we see that now 10 is less than 11, so now A is happy. Okay, so any questions regarding question interpretation? The reason why I'm going through this in greater detail is because the question is quite a lot to digest, in my opinion, right? Yeah, so there's that. Okay, so what are the bounds for each of the numbers? In this case, the bounds are n and m is 300,000, right? And k is 300,000. Basically, you're expecting a n log n kind of solution, right? Whenever you see 300,000, right? And yeah, the rest are just numbers, so they can be any number. Okay, so question now. Okay, somebody mentioned segment 3/family tree. Very good. Yeah, that's the spirit, right? Is something along that line. And namely, namely, let's start attacking the question, right? So if let's say I want to add a meteor shower, right? How do I add a meteor shower? In order to add a meteor shower, I just do if I have a segment tree over the sectors, right? So imagine I have the sectors over here and I have a segment tree over it. So I'm trying to draw a segment tree. I just try my best to draw a segment tree, the idea of a segment tree, right? So something like, if I have a segment tree over the meteors, then it looks something like that, right? Yeah, if I have a segment tree over the meteors, it looks something like that. Okay, so this is a segment tree over the meteors, and what a segment tree allows us to do, it allows us to do range add, and point query, right? Range add and range query, range add point query, things like that. Yeah, it can also do maximum and minimum, but in this case we don't need it. So in this case we can using the segment tree. What can we do now? We can now add. We can add a k value, right? We can add a meteor shower. We can add a meteor shower specifically for one of these, k equals to 1 or k equals to 2. For each one of those, right? Because it covers a continuous segment, right? Even though it might loop around, but at most there's two segments, right? But we can add a meteor shower. Yeah, so we can add, let's say k equals to 1 or k equals to 2 or k equals to 3, right? But remember, how much does each cost, right? How much does each meteor shower cost? It costs O log of m, right? Remember that there are m sectors. There are m sectors. There are m sectors, right? Log of m. So you can add a meteor shower in log m. Okay. Yeah, you can add a meteor shower in log m. So what now? Okay, let me just open this block. I'll put it aside so that I can reference the time complexity. Okay, so we can add a meteor shower in log m. Okay, using a segment tree, and you can do range thing using lazy, or you can do the Fenwick tree range update, range creating we did just now. Okay, so naive idea, right? Naive idea. Since we can add the meteor showers, right? Why not? We go through all k meteor showers, right? We go through all k meteor showers, and for each meteor shower, we add it, right? We add it, right? And after adding it, so we just naively go through all the meteor showers and add the meteor shower, and after adding each meteor shower, we go through all the states, right? So going through all the states will require O(n). And for each of the state, we look at all the states, all the sectors that they own, right? All the sectors that they own. And for each of the state, we look at all the sectors that they own. And in that case, it'll be roughly speaking, OM. And we do a point query, right? So we do a point query, which is log m, right? Which is log m. So we can do a point query in log m. Okay, so basically, how long does this take in total, right? For each meteor, for each shower, right? For each shower, we are adding it, right? For each shower, we are adding it. And after adding it, we are counting how many states are happy, right? And how many states are happy, we can do that in we can do that in OM, right? I want to say ON over here, but I want to say ON over here. Actually, in the end, it's more or less the same, because the worst case is n equals to, I mean, each state might own multiple sectors, right? But there's also a possibility that each state only owns one sector, right? So in the end, if you go through all the states and look at all the sectors, then you're gonna get OM. So I'm gonna put M over here, but one can argue is ON also, but it doesn't really affect because ON and OM have the same bounds, right? Both of them are 300,000, right? So this would be OMK, right? Log M, right? Which is too slow because there's MK over here. We need to get rid of this MK. Right? We need to make it faster. So the naive method doesn't even involve binary search, right? Remember, just going through from left to right all the showers. Okay, so question now is, there's a monotonic property over here, namely that we see that we already hinted at it over here, where when C was satisfied, right, we didn't really need to search it anymore, right? So in some sense, we don't really need to search the K equals to 2 and K equals to 3 for this C. So we don't really need to, when we process these queries, we still need to process the K equals to 2 and K equals to 3 queries for the meteor showers, because A and B might depend on them, right? A and B weren't satisfied after K equals to 1, right? But when you process K equals to 2 and K equals to 3, we don't really need to care about the C anymore, right? We don't need to query C. We don't need to do the point queries for C anymore. And the idea is that we can try to cut down that. Okay, we can try to cut down that. So the monotonicity over here, right? I'll say the monotonic property over here is that if a state is happy, if a state is happy, meaning it's collected enough asteroids or enough meteors, right? Then, so I'll say if a state is happy in that it's collected enough, right? Enough meteors. Then we don't need to keep on asking whether it's happy or not, right? We already say, are you happy? It's like, yes, I'm very happy, right? C is very happy after K goes to 1. Then K goes to 2, if we use this naive algorithm, we'll keep on asking C, are you still happy? Are you still happy? Then it's like, yes, I'm still happy, right? Of course, I already collected enough. So the idea is that the monotonic property is that if a state is happy, then then it is happy forever, right? It is happy forever. We don't need to keep on asking it. And so bracket, don't ask it anymore, right? Don't ask it anymore. And the idea is that this don't ask it anymore can help us save some time, because instead of doing OM over here, right, we expect that some of them might finish early. So this OM can be kind of put away, right? Or rather, it can be put in, it can become a K log M plus OM, something like that. Right? So we want to get rid of this. I'm just going to highlight in red. We're going to get rid this don't ask it anymore idea. It will help us get rid of this OM. Okay, any questions so far? Okay, so if not, how does it help us get rid of it, right? So here I'm gonna give you guys another observation, right? Okay, so somebody asked a question, what if none of them are ever happy? That's a very good question, right? In that case, if none of them are ever happy, we will the idea is that we loop once, right? And we go to the very end, right? And if we ask all of them whether they are happy at the very end, right, where K is equals to where K is equals to the biggest K, right? K is the last shower. Okay, so question somebody asked was, what if never happy, right? What if the states are very greedy, right? They want so many meteors that are never happy. Then the idea is that if we ask them at the very last moment and they're never happy, then we don't need to ask previously also, right? We don't need to ask all these times also. Yeah, but I understand your concern right now. It seems like we need to ask them, right? And if we ask them at every point in time, after every K, right? Then what if they reach to the last one, then they still say, oh, I'm not happy. Then you have wasted all your asking beforehand. And that's precisely the idea that parallel binary search seeks to sticks to solve, right? Basically, we're going to ask them at a midpoint, right? So instead of, okay, I think I'm just going to go straight for the idea, right? So idea of parallel BSTA, right? Okay, so to answer your question, what if they're never happy? Then the answer is that we will try to capture that they're never happy by asking them, if we ask them at the last moment whether they're happy or not, and they're not happy, then we know they're never happy before that, right? And the answer is that we'll actually query the middle first. Then we'll query 3/4. Then we'll query 7/8. Then we'll query 15/16, right? All the way until we query the last guy. So to answer your question, it's kind of like saying, what if I have an array of numbers and the last element is not big enough, right? So I'm looking for numbers that are greater than x, right? For some x. Then what if the a n minus 1, right, is still smaller than x? Then that's kind of what's happening over here, right? So you binary search here in the middle, then you ask over 3/4, 5/6, sorry, 7/8. Then you keep asking until you reach the last element. Okay, so the idea of parallel BSTA is that I'm gonna add OK, right? I'm gonna add OK over 2 first. Let me think. I'm gonna get OK over 2 first. Okay, actually this OK doesn't really matter. Okay, so the idea is that the first step, right? Let me try to think of how to phrase this in the best way. First step, right? The first step, I'm gonna ask K over 2. I'm gonna process up to K over 2, right? K over 2 showers. So I'm gonna add K over 2 showers. And the time complexity for that, right? There'll be OK log M, right? It's actually K over 2, but constant factor goes out. So I'm gonna add K over 2 showers. And I'm gonna ask, who is happy? Who is happy? Okay, I'm gonna ask who is happy. Right? And that's gonna partition my set into 2. That's gonna partition all the states, right? So all the states, A, B, and C, right? Initially, A, B, and C, they're gonna answer me who is happy. So I can ask who is happy, right? That will cause O M log M, right? That will cause O M log N by addition. So we are doing OK log M plus O M log N, right? It's not for each. I'm no longer asking for, I'm no longer adding each shower and asking all of them, right? I'm actually adding all this, then I ask. So okay, to be extra clear, add K over 2 showers without asking, right? Without asking anything. Without asking any states. Right? Then after I add K over 2, then I ask. Right? Then I ask who is happy. And some of them are going to be unhappy, some are going to be happy. So in this case, if I add until K over 2, in this case, K over 2 is K is 3, so K over 2 is 1 technically. So in this case, C is going to be happy and B is not, right? B is not happy. A is not happy. Then based on this, right, I know that my states A, B, and C, right? Imagine, okay, in this question, the K is very small, so it's a bit hard to illustrate. But if each of them have there's a K goes to 0 here, or rather the shower, the first shower, it goes to 0. I shouldn't use K equals 0 because K is technically a parameter in the question, right? Yeah, K is technically a parameter in the question. I should use I. Okay, but everything is indexed by I. So I'm just gonna say shower 1 all the way to shower K, right? Shower K. So if I up to K over 2, then the people that are not happy, right? We know that the people that are not happy, we know that their happiness is probably lying somewhere. Right? For A, which is not happy, B is not happy, and C is happy. For people that are not happy, for states that are not happy, right? We know the happiness, eventually they're gonna be happy. If they're gonna be happy, is at least past this part, right? So we know it's greater than K over 2. Right? And for people that are happy already, we know that the minimum time they're happy is before this K over 2. Right? So this is the shower K over 2. Okay, so that's the idea. Then what we're gonna do, we're gonna indicate with for each array, for each state, right? we're gonna say the range in which they could be happy in. So initially A is initially all the states are 1 to k, right? Initially all the states are, we need to search from 1 to k, right, for all of them. But after querying, after the first step of querying, of adding k over 2 showers without asking any states and then asking who is happy, we have reduced all the search spaces by half. So we know for A is going to be within k over 2 to k, and for B is within k over 2 to k, and for C is within 1 to k over 2. Okay. So now we still haven't reduced it all the way, right? But now what we can do is we can add in the second step, in the second iteration, right? This is our second step of our binary search. We can add to 3k over 4 showers, right? We add 3k over 4 showers. And basically what that will do is my A, B, and C, right? We know that A, so this is 1, this is k over 2, this is 3k over 4, and this is k, right? And this is k over 4, right? We know that A lies within here, right? And then B lies within here, and C lies within here, right? Okay, so to be more precise, I'm not adding 3k over 4 first. I'm actually adding k over 4 first without asking, right? Without asking. Then I ask the states who have the search space of 1 over k, who have 1 over k as the possible answers, right? So meaning in this case, in this example, it's going to be C, right? I'm only going to ask C. I'm only going to ask C because there's no point asking A and B. Because if I know A and B are unhappy at k over 2, there's no way they're going to be happy at k over 4, right? That's even less meteors than they want, right? That's even less meteor than k over 2. Right? So that's the monotonic property. So I'm going to only ask C, right? And C is going to return me some answer, and that helps me narrow down C's response to either 1 over k to 8 or k or k over 4 to 3k over 8, right? That's going to help me narrow it down in this way. Sorry, what am I writing? It's not 3k over 8, it's k over 2. Okay, k over 2, yeah. Oh, sorry, this is not k over 8, this is k over 4, yeah. Okay, makes sense. So if I query at k over 4, either they're happy from 1 to k over 4 or from k over 4 to k over 2. Yeah, that's more correct. Okay, then right, I'm still considering this as a second step because it's one iteration, right? Then I add from the k over 4, right? Remember, I've already added the k over 4, right? So I already added so far, right? And I can add the k over 4 to 3k over 4, right? Without asking anything again, right? And then after that, then I ask those that are within those who have ranges k over 2 to k as possible answers, right? As possible answers. In this case, I will be referring to A and B, right? A and B, right? And then from that, it really narrows that down to k over 2 to 3k over 4, or right, it narrows it down to 3k over 4 to k, right? Because I'm asking at this guy. Okay, so any questions? Okay, so that's the key idea. That's the key idea. And I can keep on continuing this, right? I can keep on continuing this, and you see in each step of the way, right? In each step of the way, I'm adding at most OK shows, right? So how many levels do I need, right? There's a total of k ranges, right? So initially I stop at k over 2, right? Then after that I stop at k over 4. So it's at 3k over 4, right? Then after that I stop at 7k over 8, right? And so on. So it's basically the sum of all these guys, which is at least bounded by OK log K, right? Because each time the search space is narrowing by at most the number of times I need to do this, right? How many times I need to search, how many times I need to add is at most is at most gonna be log k, right? So there's log k steps, right? Okay, so log k, okay, then for yeah, so it's k log k. But it's not just k log k, right? Because each step of the way, each time I process it like that, I need to each k is log m, right? So okay, so to be clearer, right? I've o log k steps, right? O log k steps times each step is ok, right? Each step is ok at best, at worst, okay? Yeah, each step is okay at worst. So okay showers, right? And times O log M for the adding of the shower, right? Something like that, right? And then question is, how about the queries? The queries will be done along the way, right? So every guy, every state, right? Every state, there's M states in total. So there's O plus O M states, right? And each state in total would need to do log M queries, right? So each state would go down this, each state would experience some amount of asking within this log k steps, right? Because if let's say I'm state A, I'm happy at unhappy at k over 2, I'll be asked again at 3k over 4, right? I'll be asked again at 7k over 8. I'll be at each level of these steps, right? I'll be asked one time. So there's a total of log k steps, right? So maybe it's best if I say plus O log k steps, right? M states, right? For each of the M states, they experience this. Okay, maybe it's better if I say this. If I move that down, right? So it's technically it's better if I say for each state they experience some amount of steps, right? I think that's clearer. So each state they experience O log k steps. Right? I'm just switching the order around, steps, and for each step, right, they experience one query, right? So this is not OM log M queries. This is more of O log M time per query, right? Time per query. Okay. Oh, sorry. M. Okay, it's actually technically not M states. It's actually N states. But once again, N and M are somewhat the same. So in total, right? In total, time complexity for this is roughly speaking, M plus K bracket log K log M. Okay. So that will pass the time. Right now, instead of OMK, we have M plus K, and then there's some extra log factors here. Okay. So that's the general idea of binary search, parallel binary search, right? Let me start from this. Let me just summarize it again, right? So once again, question was asking us, in summary, the question was asking us, each state has control over some sectors, right? And they collect meteorites on those sectors. They collect meteors on those sectors. Then we go through an example like that using the sample, and we see that there's an observation that once you have a state that is happy, he will be happy forever, ever after, right? He'll be happy forever after, right? So we want to find the exact minimum time for each state when they're happy, right? So the naive implementation, right? We don't even go through we don't even go through normal BSDA, because the normal BSDA is even worse than naive actually, right? It's even worse than the naive method. We don't even go through the normal BSDA, right? So the naive method would just be, I add all the meteorites one by one, right? I can add it using a segment tree in log M, right? It's just a range add, right? And then for each shower that I add, I ask all the N states, right? I ask all the states, are you happy? Are you happy? Are you happy? Are you happy? Right? But that's bad, right? That was bad, because we realized that if we ask a state and then they're happy already, then we actually don't need to ask them ever again, right? And okay, the reason why you can't just do that naively is because, as somebody mentioned, what if none of them are ever happy? Then we'll be asking them at every stage of the way, every stage of every new meteor that we add, right? Every new meteor shower we add, we'll be asking, are you happy? Are you happy? Then it turns out, they're actually never happy. Then what's the point in that, right? So that would be slow in the worst case also, right? So the question, the observation is that we do parallel BSTA, where in the first step, right, I call this the first step, right, where I add k over 2 showers without asking anything, right? Then I ask who is happy, right? Then I separate them into happy and not happy. So for the happy guys, I know that I need to search to the right. Oh, sorry, I need to search to the left. Right, happy guys, I need to search to the left, right? Within 1 to k over 2. Unhappy guys, I need to unhappy states, I need to search to the right from k over 2 to k. Then from there, I can add k over 4 showers without asking anything, right? Without asking anything, and then ask who is happy among the states that possibly could be happy, right? So I'm not asking all the states. This for these states over here, I'm not asking, it's not all, right? Not all, but only the only the possibly happy ones, right? The ones with 1 to k as the possible answers, right? No point asking A and B because I already know the answer for that, right? Okay, so I add k over 4, and that's step that's like step 2A, right? And then for step 2B, I ask k over 4, I add up to k over 4 meteors, right? And then I ask among the ones that have that were unhappy in the first scenario, in the first step, right? I ask them who is happy now, right? And I keep on repeating this, and in the total, if I continue with this step, so step 3, I'll ask step 3, I'll ask 1 over 8, 3. So step 3, I'll ask 8k over 8, 3k over 8, 5k over 8, and 7k over 8, right? So that's step 3. And then step 4, once again, I'll split it even further, right? So namely, how do we analyze like time complexity? To analyze the time complexity, we look at there's 2 contributions, right? One is all the showers that we're adding, right? Each time we add a shower, that is quite expensive, right? So the adding of showers, meteor showers, in this case is the blue part, right? So that's one component of time complexity. And the other component of time complexity is querying for the states, who is happy or who is not, right? But because we selected, we didn't ask too often, right? The key idea was that we must add the showers, right? Because if you don't add the showers, how can you do anything, right? But the key idea is that we can add the showers, right, in a smart way, such that we don't need to ask that often, right? So that's the key idea of binary search, is that we don't want to ask too often, because asking has a monotonic answer, has a monotonic property, right? The act of asking whether a state is happy or not is monotonic with respect to showers. So we don't want to ask too often because we want to exploit that monotonic property. Okay, so that's the key idea in this question. Yeah, so any questions? Hey, there's somebody asked, do you have an implementation for iterative segment tree? I don't actually use the iterative segment tree, but you can look at Codeforce's array segment tree. I think that's what it's called. Easy and efficient segment trees. Yeah, check this block out. This, I'm gonna send it to everyone in the meeting, right? So check this block out. It's a good explanation of what's going on. Yeah, so yeah, it's a good block. But I've never really used it personally myself. I never really needed to use it. So yeah, there's that. Okay, explain time complexity, the red part again. Sure. Okay, so the idea is that the blue part, once again, is for adding the showers only, right? It's for adding the showers. So the blue part is there's okay, so it's blue part. I think blue part I'll leave it alone. Right? For the red part is the querying of asking whether each state is happy or not. Right. So the idea is that how many states do we have in total? We have m states, right? We have technically n states, but each of the n states, they might have a few sectors, right? So this is more like m states / sectors, right? Sectors, because technically it's n states, but each state might have multiple sectors, but then the sum of all the sectors that each state owns would sum up to m. So I'm putting om over here, right? Because basically it's effectively om. Okay, so anyway, n or m, they have the same bounds. You can just think of it as worst case scenario, each state has their own one sector alone, right? Then n will be equals to m, right? So anyway, time complexity wise, n or m doesn't really matter here, right? So for each of the states, right, I'm going to ask them how many times in total, right? How many times am I going to ask them in total, right? For each step of the way, right? So this is step 1, where I add up to k over 2. This is step 1. This is step 2, where add up to k over 4, right? And I also query this one, right? Step 3, right, where I do here, 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 and here. And step 4, where I do 8 such queries, and step 5 and so on, right? Each step, right? You can think of it as a perspective of each state, right? As you're going down all the log k steps, right? You're going down all the log k steps. That's what this log k is here for. Each of the log k steps, each state is going to be only going to be asked once, right? Because let's say initially all of them are possible ranges like that, right? So they get asked about k over 2, right? Then after that, if the maybe the depending on what they answer, right? If they're unhappy, then their possible range is like that. Then in the case, we're gonna ask them at once at 3k over 4, right? Or if their state was if they're happy, then we're gonna ask them once at k over 4, right? And then subsequently we'll split it such that even though there's multiple queryings for each step of the way, right? Even though there's multiple queryings for each step of the way, but each state will either make a choice of whether it's going up or down. So let's say initially, let's say I'm state A. Let's say I'm state A, and at k over 2, I'm not happy yet. So the next time I'm gonna be asked is over here. Right? The next time I'm gonna be asked is over here. And then let's say here I'm happy. So next time I'm gonna be asked is over here. So all in all, the red dots in this case indicate the times where A is asked, right? A is asked, right? And based on whether A's answer is happy or not happy, they will be pushed either to the left or right, right? Well, the point is either left or right, and in total there's how many red dots are there in total? There's log k red dots. Okay, so yeah, so there's log k steps. There's log k red dots, right? Steps. For each step, there's a red dot where each state is asked, right? So if you can think of it as you can think of it in terms of, okay, if thinking of it in terms of active querying is a bit challenging, you can kind of think of it as an interview, right? So imagine each state went through all this trouble of answering and being interrogated and whatnot. Then after the whole fiasco is over, you go to each state and you ask, hey, state A, how many times were you queried? And the state A will be like, oh, I was queried at k over 2, 3k over 4, 5k over 8, and so on. And then you ask, okay, so how many times was that in total? Then state A will be like, oh, for each step of the way, I was queried one time, right? So I hope that analogy might help. In retrospect, right? If you think of it in retrospect, how many times is each state asked? That would be how you arrive at log k. Yeah, if you think of it as active kind of asking, maybe it's a bit more challenging because it depends on the guy's answer, right? But if you think of it as in retrospect, how many times was k asked, right? Then no matter what he answered along the way, he's always going to be asked log k of times. Okay? Because initially his whole range was 1 to k. Initially his whole range has k possibilities, and for every time you ask him, you narrow it by half. Right? For every time you ask him, you narrow the search space by half. So you need to ask somebody at least log k times, right, in order to narrow it down to a single minimum time, right? So yeah, I hope that answers your question. Anyone else has questions for this? Okay, so yeah, so if not, let's go back to this. Okay, so there's parallel binary search. There's another. I'm gonna add in uh there's a solar lamps IOI preparation. There's another one over here, which is this one. I'm just gonna edit over here. Right. So this is Ericto video. Yeah. So this is another video, but I haven't read it in greater detail, so I don't want to cover it because I'll probably be not so familiar with it. Yeah. So anyway, yeah, that's parallel BSDA. Bitmask DP, I don't have much to add here besides that it's usually used for brute force. I know there's some very interesting DPs like sum over subsets. So sum over subsets DP is a trick that allows you to do Bitmask DP, but okay, I'll just add it there. Okay, so I'll just add it here. Yeah. Sum over subsets DP, you can take a look at it. It's quite clever, but I won't be able to explain it now. Yeah. Which browser am I using? I'm using Brave. right? So it's called Brave browser. Yeah. Okay. So if not, let me just end the recording first, then we can chit chat. Yeah, so any questions for the lesson? Okay. So once again, I'll only go through the highlighted questions by default, right? Because I give you guys a lot of questions. Don't worry if you cannot solve all of them, because I gave you guys a lot of questions because I think you guys have quite a lot of time. For some of you, you guys probably will be able to finish a lot. So I gave you guys a lot. But don't worry, you cannot solve all of them, right? Do what you feel like doing. Don't need to do the highlighted ones if you don't feel like it also. Right? Just read through all the questions maybe and see which one you want to attempt, right? And give them a try. Um, yeah. So I'll try to go through the highlighted questions. If you guys request any other questions, I will read it and go through it. But try to request earlier also. Yeah, so that I have more time to prepare. Yeah. So if not, yeah, let me just end the recording if you guys have no questions. Oh, could you send the link to your... Okay, let me send the link to the whiteboard. Okay, that's a good aspect. I should send the link to the whiteboard. Okay, but it's a bit my organization of the whiteboard is honestly quite bad. So yeah, I'll say try, maybe you can watch the video if you want a verbal explanation of what's going on, because I tend to scribble all over the place. Okay, so somebody asked maybe I missed the if XOR is reversible commutative, but can we do XOR fan victory? Yes, we absolutely can. And we absolutely can, because the main property, right? Remember for addition, we have A plus B, right? The idea is that if I have a prefix here and a range here, so let's say I have a prefix A, I have a prefix A and a range B, right? A range sum B. So okay, prefix meaning prefix sum lah, and range meaning range sum, right? Then I can do A plus B, right? And that will be equals to C, the prefix sum C, right? So that's the idea. And the idea is that if I want to query, if I want to query, if I want to ask what is range B, I can use C minus A, right? The key idea is that I need to have this minus over here, right? If it's an addition, then I can just subtract it away. I need to have this minus sign over here that I can perform. And you can see if let's say we change the prefix sum over here to prefix XOR, right? Prefix XOR A and range XOR B, and this prefix XOR C, right? Then we have the same thing. A XOR B gives me C, right? Then I can do C. I can just do, if I ask for range B, I can just do B equals to C XOR A, right? And the idea is that since C is A and B, right? Since C is A and B, I can do this, and then remember it's commutative. So this is B A XOR A. Then the A and A becomes 0. Sorry, so B XOR A gives me 0. B XOR A gives me B XOR 0, which is just B alone. So the idea is that yes, to answer your question, we can do XOR fenwick tree. Yes. And the reason is because for any mathematical operation that has an inverse, we can convert prefix queries. We can go from prefix queries into range queries, right? So prefix queries is a sub-ability of range query, meaning that if you can do range query, you can do prefix query, right? Range query is just, range query means any L to R, right? So if you can do range queries, you can definitely do prefix queries, because prefix query is just 1 to R, right? 1 to I, right? Or 1 to X. So if you can do range queries, you can definitely do prefix queries, right? But if you can do prefix queries, can you necessarily do range queries? The answer is that you can do prefix, if you can do prefix queries and the operation that you're doing is invertible, right? Invertible meaning you can undo it in the case of XOR or subtraction, then you can do range queries, because you can do range queries and this would be decomposed as 1 to R, right, which is a prefix query, and then you do the inverse, right? So you invert it, right? I don't know how to denote this, but you invert it with 1 to L, and you're undoing the 1 to L kind of. Yeah, sorry, 1 to L minus 1. 1 to L minus 1, yeah. So you're undoing that. So example of invertible, maybe I just give some examples of invertible will be sum, XOR, I don't know. Any other ideas? That's the only two I can think of. Yeah, okay. So examples of non-invertible, there's quite a lot, right? Non-invertible, right? So non-invertible, there's bitwise and bitwise or, uh there's maximum. Right? If you ask a max for a prefix, that doesn't allow you to do max of range, because maybe if you do a max of prefix, right, then the maximum is here. Then how do you subtract away this guy if you want to query this range? Right? You cannot undo a maximum. Right? Minimum is also a prefix. It is not invertible. But in general, if you want to do invertible operations, let you do Fenwick, right, which is easier to code and is yeah, very easy to code, more lightweight also in terms of memory. But non-invertible operations you can always build a segment tree, right? Which is more heavy, right, to code, as well as it's more heavy to code, but the capabilities are more, because basically segment tree is two copies of Fenwick tree, right? It's two copies of Fenwick trees, and yeah, segment tree is two copies of Fenwick, one for the prefix and one for the suffix. So I hope that answers your question. Okay, if not, yeah, let me just end the meeting here, on the recording. And to answer your question, the browser I'm using, let me just end it first.